Hi, so today we'll be looking at how to use threshold FHE to reimagine trust assumptions in both CeFi and DeFi. So what actually comes to mind when you hear the words CeFi and DeFi? If you've been in this space for a while, when you hear CeFi, you probably think of Coinbase or Binance. When you hear the word DeFi, you probably think of Uniswap. But what actually distinguishes DeFi from CeFi, and is it that straightforward? So when we hear DeFi, we of course expect it to be decentralized, meaning that there are minimal trust assumptions. So we as a user don't have to put our trust in any single party for correct execution of the protocol. But we likely expect a few other things as well. We expect things to be permissionless, meaning there's no KYC. Anyone in theory can participate, and we probably also expect it to be self-custodial, meaning we, as the user, can keep control over our own funds. Going back to Coinbase and Uniswap, it's pretty obvious that Uniswap satisfies all three of these conditions, while Coinbase fails all three of them. Is the distinction actually that straightforward nowadays? I would argue that the answer is no. Looking at two more recent protocols, specifically Uniswap X and Fireblocks Off Exchange, they look quite different from old school DeFi and CeFi. Uniswap X, at first glance, appears to be DeFi. There's no KYC. It distributes trust, but you'll also notice, if you look more closely, that it is in fact permissioned. Not anyone can join in any role. When you look at Fireblocks Off Exchange, on the other hand, at first glance, it appears to be CeFi. It's permissioned, there's KYC, but if you look more closely, you'll realize it actually distributes trust across a number of parties. So what would you consider these products? Are they DeFi or are they CeFi? If a centralized entity vets participants, does that automatically make a protocol CeFi? If a product distributes trust across multiple parties, is it automatically DeFi? Even more, what happens if we introduce threshold FHE into the mix? Will it make the situation even more complex? And will it force us to reimagine what CeFi actually is? We believe the answer is yes, that threshold cryptography will fundamentally blur the lines between CeFi and DeFi. We're going to start with the simplest type of auction and see how we can use threshold FHE to reimagine it. So the simplest auction is a first-priced sealed bid auction. It works exactly like you would expect it to from its name. There is first a bidding phase, and during the bidding phase, participants submit bids which remain hidden to all other participants. In the second phase, the winner is declared, and whoever placed the highest bid should, of course, be the winner of the auction. There are two main ways in which to implement a first-price sealed bid auction. Option A is what I would refer to as the CeFi option, in which you submit bids to a trusted party or parties, and they look through them to determine the winner. Option B is what I would refer to as the DeFi option, and that works essentially in a commit and reveal approach, where participants commit to some bid, and at the end of the bidding phase, reveal their bid to determine, without any intermediary, who placed the highest bid. There are issues with both of these approaches. The issue with option A is pretty obvious. You have to trust that this auctioneer hasn't misused the bid information or incorrectly declared the winner of the auction. The issue with the option B is a little bit more subtle, and it has to do with the fact that participants reveal their bids to everyone. This might not seem like a problem if the auction is a one-off, but what happens if users are regularly participating in auctions, say for an MEV use case or for trading more generally? Well, it turns out, over time, other users can learn that individual's trading strategy. So how might we get around this problem using threshold FHE? At a super high level, you can think of FHE as an extension to public key cryptography, where in addition to being able to encrypt and decrypt data, you can now perform arbitrary computation directly over the encrypted data itself. But the secret key belongs to one specific person. When we look at threshold FHE, we now want to distribute trust across n parties. And we do this by taking the secret key, breaking it up into n shares, and distributing it to the n participants. We will not need all n of them to come back to reconstruct the secret key. We will need a subset t out of n. So how does threshold FHE differ from single key FHE? From the user side, the experience is basically the same. You might notice some added latency from the threshold decryption process, but there's no real change for the end user. In terms of privacy, threshold FHE enables what's called private shared state. So user inputs remain private, even to those sitting on the threshold committee, whereas the program output can be made public if needed to all. Things get a little bit uglier when we look at trust assumptions. That's where a bit of complexity comes into play. So what can go wrong when using threshold FHE? There's actually a lot that can go wrong, but these are the two main things people get worried about. So situation one is that the threshold committee members decrypt data they're not actually supposed to be decrypting. So in the auction example, they open up everyone's bids, even though they're obviously not supposed to do that. Problem B is that the threshold committee members just refuse to decrypt or go offline. How do we deal with these two problems? We're going to look at a committee size of 3 for simplicity and consider how to set the T value to deal with these situations. So if we have a 2 out of 3 threshold, that means we need 2 members to come back to decrypt. The great thing about this is if one member goes offline, we're good to go because we only needed 2 shares anyway. The bad problem with this is that we need to assume there's an honest majority, specifically an honest supermajority, and 2 out of 3 are honest. Otherwise, 2 members could decrypt all data, even though they're not supposed to. On the other hand, if we look at a full threshold, and this is where T specifically equals N, the good aspect of this is we really only need a single honest party to prevent bad decryptions. Bad here meaning decrypting data we're not supposed to have access to. The problem with taking a full threshold is if any single member goes offline, we're basically screwed. We have no way to decrypt whatever the program output is. So the good news is that whoever sets up the threshold FHE scheme can configure what the T and N value should be appropriately. Generally speaking, we're going to need to assume there's an honest majority or supermajority. And in theory, you can pick T and N to be basically whatever you want it to be. Generally, the use case will dictate what T and N will be most appropriate. You'll probably want to take into account, is this a long-running use case? Is it going to be going on for years, or is it just, we'll say, a week or a day or even shorter than that? If the threshold committee members decrypt data they're not supposed to, what's the worst that could happen? How could they use that data? And what sort of performance and latency do you need for your application? So how do you actually incorporate threshold FHE into auctions? Well, the new workflow is roughly going to look like the following. Whoever sets up the protocol is going to choose what the TNN value should be, and they'll have to decide who exactly sits on the threshold committee. During the key generation process, we will take our secret key, break it up into N shares, and distribute it appropriately to the N committee members. The bidding phase looks exactly like an end user would expect. They encrypt their bids with respect to the public key and send it off. The committee members wait to receive all encrypted bids, and then they run the auction program directly over the encrypted bids to determine the program output. At this point, the program output should be the highest bid, but it is still encrypted, so the committee members will have to put together their shares to decrypt that value. We have actually gone ahead and implemented this. Unfortunately, I'm not able to show a live demo, so you'll have to do with screenshots. If you would like to try it out for yourself, it's available at demo.sunscreen.tech, and it's integrated directly with Sepolia. So the demo workflow at a high level is going to look like the following. The user is going to connect via MetaMask. They're going to have to put up some stake to participate in the auctions. This is a one-time process that'll allow them to participate in arbitrarily many auctions. They will then submit their encrypted bid directly to the threshold committee members. The committee will run the auction program over all of the encrypted bids. This is done off-chain to give the best performance. The committee then decrypts the output of the program, which is the winning bid, to get who the winner is. They notify the participants of the auction, so the winner and all the losers. And then if the winning party does not pay out their bid, their stake is appropriately slashed. So here you can see that you connect to MetaMask. You go ahead and put up some stake to participate. How you determine the stake is very much outside the scope of this talk. You can think about having things under-collateralized or over-collateralized. It'll depend on your use case. You then go ahead and submit your encrypted bid. The committee members receive all the encrypted bids, and they run the auction program over them. In this case, we assume that somebody else is the winner, and it's this green box. For demonstration purposes, you're able to click on the box, see who placed the highest bid and what that value was. In the situation in which you actually win the auction, you will have to now pay out your winning bid via MetaMask. For arbitrary purposes, we've decided to give users a 10-second time window to do so. If you pay it out, everything is good, and you can continue participating in more auctions. If you don't pay out your bid, you'll notice that your stake is now forfeited, and you're capable of seeing what happened on-chain if you'd like. Once your stake is slashed, if you would like to participate in more auctions, you are now going to have to put up some additional stake to do so. So there are a few things to note with our demo and how we set up this threshold FHE auction. The first part is that there are no ZKPs anywhere in this, and there's actually no need for zero knowledge with this application. The second part is that we decided to have encrypted bids submitted directly to the threshold committee. There's nothing in theory stopping you from posting this somewhere publicly, but it adds a slowdown that we believe is not necessary. Finally, we also think it's best to run the auction program off-chain, and you'll see why shortly. But to get good performance for the user, you actually need a decently beefy machine. So because the numbers are actually quite complicated when you have threshold FHE, so specifically the setup we used in our demo is 2 out of 3, and all 3 members are located in the same region. We've decided to just give numbers with single key FHE. If you would like more detailed threshold numbers, feel free to approach me after the talk, and happy to share them. But the runtime on a 64-core machine for an auction is around 2.1 seconds. If you use a consumer laptop, like a MacBook Pro, you're looking at around 8 seconds. There are a lot of parameters to play with to get the performance down even further. So one interesting question you might ask is, do you actually need 128 bits of security? If it's an auction that lasts for 2 seconds, you probably don't. So can you drop the security to something like 80 bits? Another interesting question is, what sort of precision do you actually need for the auction itself? Do you need 64 bits, 32 bits, or can you drop it further? Because the further you drop it, the better perf you'll get. Finally, another interesting question with FHE is, what sort of error rate are you okay with? Are you okay with a 1 in a decillion chance of an error, a 1 in a billion chance of an error? If you're okay tolerating a higher error rate, you can get better and better performance. So what lies in the road ahead for threshold FHE? One interesting question to ask is, can you use other privacy techniques to provide better privacy for the user? Can you get them anonymity? Can you disguise deposits into that collateral contract? Another question you might ask is, why do the committee members have to run the FHE computation? They don't technically need to do so, but it certainly simplified things for our demo. One question you could pose is, why not have validators run the FHE computation and separate out duties so that the threshold committee is only responsible for performing decryption? Finally, there's the natural tension between performance and decentralization. How many members need to sit on the threshold committee to be decentralized? 10, 20, 50, 100? So the natural question we asked ourselves in building out this application is our threshold FHE auction CeFi or DeFi? But honestly, does it really matter? Thank you so much for listening. If you'd like to try our demo, feel free to find it at demo.sunscreen.tech. Unfortunately, you cannot use a phone to access it. And if you would like to learn more about us, a QR code for our website is up top. So single key FHE is when one person owns the secret key versus threshold FHE is when we've split up the secret key into different shares. So I can already tell you what the numbers are for the actual demo itself. So there we have a 2 out of 3 scheme, and the top number blows up from 2.1 seconds to about 2.9 seconds.
That's not that bad.
Things get a lot worse if you want to look at, we'll say, like 50 members.
And how complex are the computations that you could do? Like, it's fully homomorphic encryption, but how difficult, like this is an auction, right?
Yeah.
But in general, how difficult are the computations that you can do with threshold FHE?
So in theory, there's nothing stopping you from doing super complex computations, but the overhead will get worse and worse. So a different demo we have is actually a dark order book, which runs a more complex matching algorithm. You'll find that the times for threshold FHE there are quite ugly. You're looking at, on a 64-core machine, something like 8 or 9 seconds to try to match orders together, assuming there's 50 bids and 50 asks. But we didn't run past, we'll say, 8 or 9 parties. So like 50 plus parties, no idea what the times are and how bad they are.